Okay, so here's the last topic or two. So when we talked about periodic trends, what have we talked about so far? We've said effective nuclear charge, right? Effective nuclear charge is the justification for the atomic radius trend going from left to right. We talked about ionization energy, right? How difficult it is to remove an electron is based on the strength of attraction between the electron and the nucleus, which again is dictated by effective nuclear charge. In a sense, it could be related to atomic radius as well, but atomic radius is more like a secondary argument. The primary argument would be effective nuclear charge, at least if you're talking about left to right. Vertical trends, so the vertical trend for radius would be based on energy levels. The vertical trend for ionization energy would also be essentially Coulomb's law and distance. So electron affinity. This is kind of a weird one. So it's defined as the energy change associated. So the energy change associated I have to switch pencils. Okay. It's the energy change associated with the gaining of an electron. Specifically, the gaining of an electron. Okay? So, in simplest terms, if we look at this equation, here is element X. X gains an electron, right? When anything gains an electron, of course, it's going to become a negative ion, right? And so, in this example, whatever the delta E is, whatever the change in energy is, that is the electron affinity. Now, the electron affinity can be a positive or a negative value. All right, so for example, something like chlorine gaining an electron to become chloride. So what do we know about chlorine? We know that chlorine is a nonmetal. Would you say chlorine has a relatively high effective nuclear charge? Yeah, it's in column 7 or 17, right? So it's all the way to the right. It's got an effective nuclear charge of +7. So chlorine is very likely able to draw an electron towards itself. The smaller atoms with high effective nuclear charges do very well at attracting electrons. So when this forms a chloride, the delta E is going to be negative. And remember that negative means a release of energy. And if we were to look at an energy profile for this process, okay, so if we just simply plot a very simple diagram, energy, and let's write progress. We write progress instead of time because we're not literally measuring this with time. We're just showing a before and after. So here's the chlorine atom. Here's the chloride atom in terms of energy. All right, there's a change in energy here. All right, the delta E is negative. So anything that releases energy results in a lower energy state. Lower energy states are more stable. Okay? So another way to think about this is when bonds form, energy is released. It's not obvious, but there is a bond forming here. What is it? Or I should say attraction. An attraction bond, that's semantics, which word we use here. What's happening? Yes, there is an attraction forming between the chlorine atom and the electron, right? The result of which releases energy. Anytime bonds form, it is exothermic. The forming of bonds releases energy, okay? So this particular process here makes sense. And if I were to draw another one here, okay, so let's say iodine. All right, let me actually pick a color, it's different. Iodine, and gaining an electron to form I minus. The energy profile might look something like this. Observations about this energy profile relative to chlorine.
It's less exothermic?
Yes. The energy change is less. Okay, so we can still call this an exothermic process, but in terms of magnitude, it's not going to release as much energy. Now, what is happening here? When the bond forms between chlorine and an electron, right, that amount of energy is significant. But when a bond forms between iodine and electron, you do release energy, but it's just not as much. Any thoughts as to why there would be a difference? Ron, what do you think?
Well, iodine has more energy levels than chlorine.
Yes, it does. More energy levels, yep.
So if you add an electron to iodine, it's still going to be farther away from the nucleus, so not as much attraction will be formed, so it won't release as much energy.
Yeah, that's right. The electron, the bond, the attraction that forms between the electron and iodine cannot be as strong as it would between chlorine, because chlorine, the electron gets a lot closer to the nucleus. With iodine, it doesn't get as close to the nucleus because iodine is a large atom to begin with. All right, maybe to put this into pictures. I really should have spaced this better. Okay, so we'll do this. We'll do this up here. So here's chlorine. All right, so here's iodine. So yeah, that's bigger, right? Everyone see how the iodine ion is larger than the iodine atom? Is it dramatically larger? I would say it's not as large. It doesn't increase as much in size as the smaller one does, right? So, but more to the point, the electron, the distance from the nucleus to the distance between the nucleus and that newly added electron is greater in iodine, which means iodine's electron does not get as close, does not form as strong of a bond, does not release as much energy. So, following this trend, what would your predictions be for bromine?
Not as exothermic as that of chlorine, but probably more exothermic than iodine.
Yeah, somewhere in the middle. Somewhere in the middle. Okay. Now, I want to, for the record, okay, you might be thinking about this in terms of, oh, halogens have 7 out of 8 valence electrons. That means to gain 1 electron makes it stable. That's why it releases energy. And I'm telling you right now that that is wrong. That is not an acceptable answer. Okay? Things just don't click just because now something has 8 out of 8 valence electrons. Okay? The concept of valence electrons is a construct. It's a mathematical pattern that we devised to fit our observations. Okay? That is not how you explain this. You explain it primarily based on the laws that we have mentioned, okay, and the terminology. Effective nuclear charge, Coulomb's law, right? Those are proper uses of terms for explanations, not that something has, now it has, 8 out of 8 valence electrons. That's something that is sometimes taught to sophomores because we don't go into the same depth with the terminology sophomore year, okay? So I'm telling you right now, if I see that, that's just wrong. I'm just going to mark it wrong. I'm not even going to read the rest. Okay? It has nothing to do with getting 8 out of 8. Okay? It's all based on the facts. And the facts are the distance, the charge, right? The strength of effective nuclear charge. Those are facts. Okay. Let's take a look at another example of electron affinity. I'm going to have to wedge a page in here. Okay. So something like this. What is happening here? Is this something you have seen in this class? Through experiments in the lab? No, you've never seen this. Never in the lab, never in a worksheet, never in any notes. Because it doesn't happen, right? It doesn't happen. Why doesn't this happen? Well, for one thing, metals barely have enough of an attraction to hold on to their own electrons. Thus, their ability, if they can barely hang on to their own, what do you think the likelihood is they're going to be able to take an electron from somewhere else? Not, right? This is going to be a positive electron affinity because this is it's going to become less stable by trying to juggle an additional electron that it cannot grab onto. So it just doesn't happen. And you can pick any metal, and for the most part, nearly all of the metals that you see are going to have a positive electron affinity, which means it's not likely. That is why we don't encounter negative metal ions. Right? Their electron affinity, their ability to grab and pull electrons, are a term called electronegativity, which we're actually going to talk about in next unit. Okay, but electronegativity is the ability to draw electrons towards itself, and metals are the worst at it. They just can't. They can't pull electrons towards themselves. Okay, so less stable, and processes that result in things being less stable are less likely to happen. Okay, disambiguation. Let's talk about differences between other scenarios. So let's talk a second about ionization energy again. Here's an example of an equation representing ionization energy. Definition of ionization energy is the energy required to remove an electron, and that's what's being represented here. We are removing an electron from an element in its standard state. Does that make sense? So the delta E would be equal to what's called the ionization energy. Technically the first ionization energy. But what if you saw something like this? Again, well, in this case, this is something you probably will never see, but for the sake of hypothetical discussion here, what would we call this? Well, yes, this represents the second ionization energy, right? So, is the first reaction likely? Yes, the first one is likely. The second one is not. What is the reason why the second one is not likely to happen? Correct. Sodium only has, so 1s2, 2s2, 2p6, 3s1. Sodium only has one valence electron. So this electron being removed represents this process. Right? But if you were to try to remove a second one, so this process here means you're removing one of these, and that's considered a core electron, but more importantly, it's just so much closer to the nucleus compared to the third energy level electron that the energy cost is going to be significantly higher. Is it possible? Yes, it is. It is possible. through photon electron spectroscopy. When we bombard atoms with X-rays, we can knock all the electrons off, right? And in doing so, we can calculate how much energy it took to do so. And we will see little peaks on a chart. And we'll assign peaks as to which subshells they are, right? Okay. All right. So that's what I want to talk about as far as electron affinity, ionization energy. So the last thing, transition element behavior. Okay. I'll explain this. This may take some time to sink in. Okay. Here, actually, I'm going to go back to this page here that I made more room on. Okay. So, remember how we said for elements like transition metals like scandium, titanium, vanadium, all of those transition metal elements, D-block elements, right? So scandium is 4s2 3d1, right? Titanium is 4s2 3d2. Vanadium 4s2 3d3, right? And remember how we defined valence electrons? The highest energy level electrons. And generally we call them the outermost electrons. And so if I said to you, all right, how many valence electrons does scandium have? What do you think? Yeah, just two. These two. Gotta make that bigger. Okay. What about titanium? How many valence electrons does titanium have? Also two. Vanadium? Okay, so we've already discussed that 2 seems to be the default number of valence electrons for D-block elements, right? And the justification is that they are the highest energy level. They are the highest energy level. It's 4s. But why is 4s higher energy than 3d? Why is 3d come after 4s, yet 4s is higher energy? This has always been confusing. When we looked at that chart, any chart, the fill order diagram, the one with the arrows, the 1s2, 2s2, 2p6, that one, why do we even have that? Why do we need something like that, a device like that, to help us figure out the order of electron fill? But then when we're removing electrons, we don't remove them in the opposite order of the fill. Because if we did, we'd be removing the 3d electrons. So this has always been confusing, and the reason has to do with what's called penetration. You see, an S subshell is a sphere, right? And the key component is that it has no nodes, right? In the XYZ coordinate plane, there's no node. And remember, node is an absence of presence. D's look like this, right? Remember how they were like oriented the different ways, right? And they essentially look like X's, but they're kind of laid out. And then you got the donut. So the 5D orbitals, they all have nodes. So if the nucleus is at the node in a D subshell, D electrons, there's a limitation as to how close D electrons can get to the nucleus because of that node, right? They can only get so close. So D electrons don't get close to nucleus due to the waveform nodes. We talked about how the electrons move in waves, right? And the specific wave in which they have to travel does not allow them to get that close to the nucleus. If it never gets close to the nucleus, then it just never really it cannot lower its potential energy very much. Because if the electron got close to the nucleus, that would be a formation of a strong attraction, and that would release a lot of energy. But the fact that it just can't means it doesn't really lower its energy very much. Now, taking a look at the s electrons, there's no node, right? So if the nucleus is here, right? If the nucleus is there, the electron has free reign to go as far out as this or as close as this. So it's just kind of, making itself at home, going wherever it pleases. The truth is, the s electron has a wide range. It ranges out farther but also can get close to the nucleus, lowering its energy, potential energy. So, I go back to the 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, and so on. And when we fill this diagram, this order of fill is based on the Aufbau principle, which is low energy. So according to this diagram, what has lower energy, 4s or 3d? 4s on average has lower energy, okay? So that's why we fill 4s first. But if I am now going to be removing electrons, even though 4s has lower energy, right? And so, and by saying 3d has higher average energy, it sounds like 3d would be easier to remove an electron, but that's not the case because 3d is tucked underneath the range of the s electrons. So if 2, 3, okay, so if this, if the yellow, if the yellow represents the range of the D's, the s electron range, because it ranges out farther, it's easier to remove an s electron because the s electrons put them out there. They put themselves out there. They're able to run closer to the perimeter of the atom, whereas the D's never venture close to the edge of the atom. The s's, they're just easier to grab because they extend outward more. Even though on average they have lower energy, the reason why they have lower energy is because they get closer to the nucleus. But the fact is their range is wider and thus easier to remove. Yes, Rowan?
So why is it when they go closer to the nucleus they get lower energy?
Well, what's the charge on an electron?
Negative.
What's the charge on a proton?
Positive.
So when take two things opposite charges, put them close to each other, what happens?
They get attracted.
They attracted, and then they're forming a bond. What happens energy-wise when
It's released.
you release more energy? Yes. Okay, this is a weird topic, so this might take a day or two to sink in. All right. So, hey, I'm recording this. You get to watch this all over again at your own leisure if you want. Okay. And we are done with that, so we're going to stop here.